bias example. The point of this exercise is to try to accelerate the process of simulating by playing cards so that the computer can do all of the work for us. So what I'd like to illustrate here is how we can use a Colab notebook in order to accelerate this simulation. First, I'm going to import pandas as PD and seaborn as SNS, which is a typical beginning for statistical work. The first thing we're going to do is we're going to create a sample. The sample is going to be a pool of 48 people, and we're going to represent this as a list. Now, they don't actually have to be women, and they don't actually have to be men. They just have to be the kinds of things that can be distinguished from one another. So what I'm going to make is I'm going to make a list of 24 ones and 24 zeros. The ones will code women, and the zeros will code men. So when I make this pool, then I just get a list. And if I ask to see the list, then I'll just get this long list of zeros and ones. Now, this is just a list, not a pandas series, and we might be better off if we make this a pandas series. So let's turn that into a pandas series. And now we have a pool. It's simply a small data set with 24 ones in it and 24 zeros in it. We could do pool.describe and it would be totally boring, right? The average is about, well, the average is exactly 0.5, right? Because there are zeros and ones. Okay, so that's the pool from which we will select. The next thing we need to do is we need to randomly select 35. Now, the pandas series has a nice convenient function called sample, and we can sample 35 from this. So this is what happens when we sample 35. These correspond to the mixed red and black cards in the sample, and they need to be counted. Now, because I've been a little bit sneaky here and coded this as ones and zeros, it's pretty easy to count how many ones there are. In fact, there's a built-in function that will count how many ones there are. We can get that number by simply adding up all of these values. If we add up all these values, we're effectively counting the ones. And so I'm just going to sum these values. So that gives us 16. Now I'm going to re-execute this line, and you'll notice that something strange will happen. When I execute this line again, I'll get 19. So why did that happen? Because sample is a random sampling function. It randomly samples 35. And so we got a different random sample. Notice that 16 and 19 are both pretty close to half of 35, which is 17.5. And this reflects the fact that if we are in a completely unbiased way, selecting 35 from 48 for promotion, then the number of women recommended for promotion will be approximately half of 35. If I execute this line again and again and again, you'll see that mostly these answers are close to 17 or 18 with a little bit of high and low variability around those values. Now, I don't want to just do this a million times. I don't want to hit this button a whole bunch of times and record the values. So what I'm going to do instead is I'm going to tell the computer to repeat this for me. So I'm going to put this in brackets, and I'm going to make a loop. This loop is kind of big here. I'm going to make this happen for 10,000 times. So when I execute this line, I will do 10,000 simulations, and I'll get back the results. And look at this long, ugly list of results here. This shows me lots and lots of results. And of course, it's cut off. It says ... right? 10,000 answers to this question. Now, looking at them just by eye was not exactly what I wanted to do. So let's again make a pandas series about that. And then we'll start analyzing that pandas series. So here we'll build out basically the results of 10,000 experiments. And then we want to have a look at those results. So now I'm going to do a distribution plot of the results, and we'll see what should we get. So is this a surprise? Well, notice that every time here we get a whole number. So this thing jumps up and down just because we don't have any decimal numbers in between these whole numbers. But notice the basic bell curve shape here, the imperfect bell curve shape focused on these two values, 17 and 18. That should not be a surprise. What that means is when we 10,000 times ran this experiment, the most likely results were 18 and 17, which is exactly what you would expect from this experiment, and it's what I got by hand when I was shuffling the cards. Notice, however, that 16 and 18 also appear fairly frequently. They're the next closest values to 17 and 18, so that makes sense. Notice, and this is interesting, the value 14 appears a non-zero number of times, right? We can't tell by the y-axis exactly how many times it appears here, but the value 14 appears. Why? Is this because of bias in the process? No, this can't be because of bias in the process because the process was completely random. What we're seeing here is it is possible for random coincidence to cause the results to give us 14 women promoted. Why is 14 so interesting? Because that's the value that came in the actual data set we were looking at. 14 women were promoted and 21 men were promoted. And this graph shows us that it is possible that coincidence is the right explanation for that. Coincidence can lead to that kind of unfair outcome. So how do we evaluate whether this is most likely due to coincidence or most likely due to something else? Well, we need to ask ourselves, yes, coincidence can explain that, but what are the chances? Well, I've just done this experiment 10,000 times. So all we need to do is count up how often we got results that were like those from the experiment. Now let's look very closely at these value counts here. Notice that 17 and 18 are the most common results, and that they've happened, some 2,000 odd times out of 10,000. But notice that 14 and even 13 are also possible in this simulation. Now, 13 certainly would have counted as evidence just as strong, even more so, in favor of our alternative hypothesis that the managers are biased. So when we're asking ourselves, what are the chances of getting evidence like ours, we should include any coincidental appearance of a 14 and any coincidental appearance of a 13. And if we had any 12s, we would include those too. So what we're doing here is we're identifying how often coincidence can cause results like those that we've witnessed. And the answer is 221 plus another 32 have given us results just as strong as those that were actually witnessed in the study. And so we're going to take the number of times we've gotten results just that strong, divided by the total number of simulations we've done, and that will give us the p-value, which if we want to see it, we should put it on its line by itself. And notice the p-value is 0.02. So it can happen, and it does happen about 2.5% of the time, that simple dumb luck in the presence of unbiased managers will give us results like 14 women were promoted and 21 men, or results like 13 women were promoted and 22 men. It can happen, and it does happen, but not very often. This is about 0.02, which is about comparable to me guessing the right card from the whole deck, right? This is a 1 in 40 probability, more or less. Now, that value is so low that although we see it as a real effect, we discount it as not a very probable effect. This value is smaller than our standard threshold of significance and our tolerance for believing in coincidences, which is 0.05. And because 0.02 is smaller than 0.05, we now have the information we need to make the judgment about these hypotheses. The judgment that we will make is this p-value is very small. Coincidence is not a good explanation for the results. The null hypothesis is therefore not a credible hypothesis. And so we will conclude the p-value is small, the null hypothesis is not credible. We will reject the null hypothesis, and we will say we have statistically significant evidence for the alternative hypothesis. What is the alternative hypothesis? The managers are biased. So in this study, even though the sample size was only 48, because of the strength of the results, 14 versus 21 women promoted, we actually have a p-value which is very significantly small and gives us a statistically significant result. And this is how we can conclude with statistical confidence on the basis of the p-value that the managers were indeed biased.